So I'm turning off my camera.
Yeah, okay.
Is it okay?
Yeah, you can put it on if you will be asking questions.
Yeah, just
If you will
turn off.
Okay, yes, it does make sense.
Okay, but I'm online.
Yep, okay. Okay, welcome. Fatima, if there will be noise, you can switch on microphone and put it on for asking questions. If there is no noise, keep it on.
Okay.
Thanks for joining the meeting. We have a special speaker. And the main goal is to evaluate the ideas logically and try to provide feedback. I know the speaker will tell better what it is. So it's we have a special guest. It's protocol of today's meeting. You are welcome to edit it with red pen, tell what is wrong according to your opinion.
Okay.
If you want to.
Yeah.
So, tolerance in quantum dots.
Yeah.
Positive and negative. So yeah, as Dimitri introduced, my titles, some of it got cut off, so I'll go over this in more detail when I start. But previously, I've been looking at polarons and lead halide perovskite materials, specifically quantum dot, and we got some interesting results from that, looking at the spectra of individual polarons. But now we want to go another step further, because in reality, when you photoexcite these materials, it creates positive and negative charge at the same time, so you have to account for simultaneous positive and negative polarons in the material. And so that's what the bulk of this talk will be about. And a lot of it is preliminary results for doing our ground state calculations, or what we'll use for our dynamics in the future. And I guess the big methodology increment that we're trying to incorporate is including dephasing effects in these materials, because for things like polarons, it's expected that due to screening of lattice interactions, that dephasing should be slower, and consequently the lifetime should be longer significantly than when you neglect them. So those are kind of the main highlights that I'll be talking about. And so what's been done so far? So this is the first, or one of the first papers that we published, just looking at traditional photoluminescence in these materials. So you photoexcite it, and then we modeled the hot carrier dynamics when it cools to the band edge, and then computed the competition between non-radiative and radiative recombinations of the band edge. And we computed a theoretical quantum yield of 56%, which is a little lower than what they see in experiment, but it's on the same order of magnitude. And then, so that was one of the first projects. And then the latest project I've mentioned earlier is we looked at individual positive and negative polarons. And so when you put in a negative charge, it reorganizes the lattice around it and creates a little potential well for the positive and negative charges. And then we looked at possible IR spectra, because within like the potential well, they are like dipole active.
So it's electronic transitions in the IR diapason.
Yes.
Because a lot of people think of IR only vibrations.
Mm-hmm. So it can non-radiatively move as IR, but it can also emit an IR photon as well. And the camera, the screen here kind of blocks that, but we try to compute photoluminescence yields within the potential well, thinking that if you get like a population inversion, you could get IR lasing or photoluminescence out of them, which would be competitive because there's not a lot of materials that can do that at room temperature. But we found that they had relatively low yields on like order like 10 to the -4. So it's an inefficient process for generating photons.
How do you define your quantum efficiency in terms of your rates?
So we just assumed it's like, I don't know, just considering radiative and non-radiative. So it's the radiative rate divided by the sum of radiative and non-radiative. That's kind of one of the general definitions of quantum yield. So
Rate, I mean, to determine rate, I mean, do you fit exponential or?
we compute matrix elements for lowest energy transitions, and so from those matrix elements we can get a rate.
Right. So rate, I would expect is something e to the minus r times t. That r there is.
So yeah, they're all assumed to be like just two levels. So it's two-level interaction. So it could be considered as like a state-to-state single exponential rate. And so what we want to do is look at these same possible radiative and non-radiative transitions in more detail. So what we want to do is incorporate both the positive and negative polarons at the same time, and also account for inclusion of dephasing during the trajectories. And so essentially what we're going to do is create a 4-state model that we're going to parameterize from DFT calculations. So essentially we create polarons. So like the lowest energy polaron would be putting an extra charge from the lowest from the HOMO, putting in the LUMO. So we get these states, and then to create like the P band, which we label as like similar as you would for atomic spectra, so SPD. So for the P bands, we just put occupations in those higher bands to get those states, and then the end result is we should be able to compute the radiative and non-radiative transitions from like a hot polaron for these PE to SE and pH to SH transitions, and also potentially model like radiative recombination of the polaron across the band gap. So this SE to SH transition.
So that P doesn't have to do with angular momentum, what does it?
It does. So that's.
So you take the state and you determine that it mostly consists of L equal 1.
Mm-hmm. And so kind of illustrate the fact, so these two models here are from orbitals computed from DFT. So if you consider like in quantum dots, these S and P orbitals will show up in the envelope portion of the wave function. So for like what we would consider our SH, our HOMO, should be circularly spherical. And that's roughly what we see from our modeling. And then for the P bands, you would expect to see like a nodal plane. And we see that if you turn it at the right angle, you can see that like, the density goes to like a minimum near the center of the dot.
Why only 2 states? Is it technically challenging to include like
To do the conduction for plot orbitals for these ones? Is that what you're saying?
Yeah, I mean usually you take some active window that covers some suitable energy range.
Mm-hmm. Well, I mean we could go higher, but when you include coherence into your excited state dynamics, that increases the computational time. Like I think without including it, it scales like n squared. But when you include coherence, it scales n to the 4th. So you kind of want to reduce the orbitals, the transitions that you look at. And the ones that we're most interested in are the ones in the well. So if you consider like the lowest like hot polaron, which we would call this PE band. to see if we can get efficient photoluminescence from those transitions.
And those sub-gaps are sufficiently large. They're bigger than any other sub-gaps in the rest of the band.
Yes. So it's similar to like the hydrogen atom. So like the energy difference between the lowest bound state and the next highest state is fairly significant.
And I'm also curious, since you look at the orbitals, so where are they localized? Are they localized in some specific atom? They're all over?
So there are, it's not necessarily localized on an atom necessarily.
So it's truly collective.
So it's like a particle in a box. So it essentially, you have electron density that decays near the edges, and then it.
So that bounding box, is it, really the simulation cell in DFT or?
With some vacuum.
So it's a cubic semiconductor nanocrystal.
Yes. And so you do the contributions from like each.
I have a question.
Yes.
As P and S means S and P orbitals.
Loosely. So it's like, so they have like S and P symmetry for their wave functions. So it's analogous to like S and P for like hydrogen wave functions.
But it is not localized on a single atom. It is an envelope of an orbital that includes atomic densities on like hundreds of atoms.
So like each, so if you consider like a wave packet, it has the fast and slow components. So the slow component would be like the envelope on the entire outside. Then the fast component would be each atom center.
Okay.
And your p orbital that you are drawing on a lower edge, is it 3 degenerate if you keep plotting other orbitals?
Roughly. So they're not fully degenerate. There's some energy splitting.
But shape of next 2 orbitals will also have the p envelope oriented in different direction.
Roughly, anyway. Some of them, the nodes aren't as visually apparent, but you can still see that there's behavior that you'd expect.
But you kept only one of them, right? There should be 3 of them, right? So the other 2 are sufficiently high in energy?
Not sufficiently. So I guess, yeah, there is a degeneracy issue because they're within like room temperature energy.
Also, I'm sorry, since we've been such a productive discussion. So, are the states from DFT or are they? Right.
So so they're just illustrations right now, but we do get these we compute the electronic structure from DFT.
Right. But then you only keep the 2 levels in the conduction and 2 levels in valence. Was it something more?
I guess we haven't actually done the dynamics yet, so it's still up in the air how many to keep. But I only.
No, those 2 horizontal lines up there and down there.
Right.
That means that you have 2 levels. Right? Or am I?
Yes, so that's what that image implies, yeah.
It is what the image implies,
Right.
but the question is deeper than it sounds from the first time. The p orbitals are triple degenerate, and if one wants to be very rigorous, one needs to use 4 orbitals in each band.
Yeah.
And then if you go already quite complicated.
So which ones do you throw away if they degenerate?
The bad ones.
The ones who don't do it.
Well, I guess it's still an ongoing project, so we haven't thrown any out yet. I've only computed, up to this point, I've only computed just static structures with just changing the occupations.
So it's not a report of accomplished project. It's like research directions with some intermediate results.
Yeah, I'm not worried about status. Also, since all these bits and pieces rattling around, so you said envelope function. Is block theorem somehow coming here?
Mm-hmm.
How?
So,
What is it? I mean, it's an isolated aperiodic structure.
mm-hmm, so it's so if you assume particle in a box, and if you try to put a plane wave in the box, it will just, like in Bloch functions, that phase factor, it's like it will just create a standing wave because it reflects back and forth off the edges.
Superimposing phase factor from forward going and backwards going waves, one obtains envelope function, right?
Well, I have been blabbing about Bloch's theorem and until I'm blue in the face, as you know, you've been sitting there. And, for me, it makes sense if I have a periodic structure. Okay, I understand. So where is the periodicity here?
So it's within the periodic part would just be the atom centers. So that's it's not totally periodic because you have defined edges.
Okay, so can you articulate the approximation here? So you treat this as a periodic structure, boundary effects, surface effects notwithstanding, or what?
Well, I guess I don't treat it. I mean, DFT does the calculation, so it's like I don't treat it as anything. But I guess if I wanted to do it by pen and paper, it's like I would write out my Bloch's theorem. So it's the u of x with the exponential, and then if I look at the density, that exponential turns into reflecting wave. So you have positive and minus phases that cancel, and you get the sine squared term, which you'd expect for a particle in a box.
Sure, yeah.
So that's how I conceptualize the DFT results, or what DFT computed based on the orbitals and the energies that they give. I guess I've tried doing it by hand and paper, but it's I get terms I don't know how to deal with because it's easy to deal with the envelope part, but then there's the u of x terms, and since it's not periodic, I'm not quite sure how to deal with them.
I don't want to hijack the conversation or anything, but it seems to me it's either one way or the other. Either you somehow approximate it as a particle in a box, or you do DFT. It produces you Kohn-Sham orbitals, which you can take. You can determine that they're mostly, of P character or S character. And so that's one way of doing things.
Mm-hmm.
And another way of doing things is to, bring in Bloch theorem somehow with pen and paper. Which way is it?
Of course, first. Isn't that clear from the presentation?
I thought it was, and then I still don't know how the Bloch's theorem comes in here.
It is involved only in the interpretation.
I see. Okay, that's good enough for me.
Good.
Interpretation. And how big is this system? Is it huge or what?
It's 1,200 atoms.
Okay, so it's pretty big.
For this system. So yeah, so this is just illustration to show S and P because it's more visible on these models. And then the other model that we do the actual calculations on, it's still 1,000 atoms.
I mean, you look at the just Kohn-Sham spectrum, it's going to be pretty dense near Homo Lupa, isn't it? How do you manage to get away with just, taking two and just...
Well, for the conduction band,
It is what it is. They're not dense at the edge.
Okay,
There are some gaps.
so they are not.
It's objective observation.
Right. Okay, that's great. That's good. So the rest of them are kind of isolate, separated by something else.
Mm-hmm.
And they're not associated with any particular atoms. They're really this collective states.
Mm-hmm. If it was localized to like one atom, it's like it'd be fairly easy to see because you just have like these yellow spots just at like one of the atoms.
Okay, look, I'm sorry to hijack. I do hate it when it happens. I've been hearing about this for some time. Please do proceed.
So that's the plan. Radiative and non-radiative transitions with including coherence eventually, or including dephasing into the dynamics.
What is NC mono?
Nanocrystal or quantum dot. Well, it seems like the computer's froze because even on
Try the mouse.
the mouse. Oh, here we go. And so the ultimate goal, or the most competitive aspect, will be including dephasing and decoherence effects into this model. So I thought it would give a little description and some intuition about how dephasing will occur in atomistic rates, or atomistic based dynamics. And so my first slide, I'm considering if you just have a two-level system just isolated by itself. And I say isolated because, in parentheses, because we're going to give it a pi pulse, or optically excited, so you create some changes in occupations for your two-level system. And based on the Liouville operator, when you include white matter interactions, that you're going to see a change in your occupations. And so this blue line is fully occupied after the pi pulse. Both the levels are half occupied. And you see that these dotted lines represent the coherence or off-diagonal elements of the density matrix. And then they spike with the optical transition from the pi pulse. And then if you could somehow isolate the system after inverting it.
Oh, you're showing everything before time zero and after time zero, so to say.
Yes.
Or zero plus delta.
Mm-hmm.
Okay.
Because before I had it in one slide and it was...
So you just chopped onto pieces.
Right. And so then now if you could fully isolate it without it interacting with the environment, the off-diagonal elements will continue just oscillating, assuming that there's no changes in the occupations.
So just because of accumulation of phase.
Mm-hmm. And so the two states stay in phase, so they stay coherent with each other. And so that's kind of like the goal for things like quantum computing and even energy transfers, is obtaining very long coherence times.
Can I scratch weak side?
Sure.
Can I, one slide back. So when you symbolize pi pulse with this little bug sitting on the x-axis near zero in 0.00, it looks like several oscillations of electric field up and down, with very tiny period of each oscillations. So it looks like one thing, but it seems that it is collection of oscillations of electric field. So very high frequency. And then on the next slide you have keep it here for time. On the next slide you do have oscillation of off-diagonal elements of density matrix, which happen with very long period. So it is what is shown on the figures. On the other hand, it is assumed that pi pulse, in order to promote elevation, should be in resonance with frequency energy offset of these levels. So this frequency of optical pulse and phase accumulation should be the same. Why they look drastically different in these figures?
I think I'm fairly confident it has to do.
And it is more like an exam question. There is a strict answer, and it doesn't deal with the rest of the research.
I think it's just how you define the problem when you're writing everything down. So you can evolve systems in different frames, and in this case, it's like the wave packet is like the wave packet. You have to have slow and fast components to make such a narrow pulse. And so mathematically that's complicated to deal with, so it's easier just to have your system move with the slow mode, and then just discard the fast high frequency.
So it's rotating wave.
Yeah, rotating wave.
And maybe there is also a rotating frame, like observer sits in the oscillates with this E1 minus E0. And the slow oscillation of the off-diagonal elements is just a little deviation from average.
Yeah, I think we actually did this in lab. If you go to the non-rotating frame, it's the same. Same, but it's just you get little squiggles, so it's small deviations. So on average, the phase follows this trajectory.
It's
Maybe
rotating.
I'm imagining that.
Two different things: rotating wave approximation and rotating frame. And we may never went away from rotating frame because it will make complications much more expensive, and one would need to take 100 times smaller time steps.
It's the rotating frame approximation.
Okay, please keep going. It's just a little note that we're going to discuss it now rather than review or ask
It's
it.
getting dark and scary. Scary, it's dark. Going to be soon, very.
So that's a huge.
Master Jordan.
Dark it will be. Yeah, dark it will be soon.
So this slide's a little busy, but so previously we had our two-level system isolated, but now we throw it into a heat bath. So it's basically just connected to a bunch of harmonic oscillators with different potentials. And you take the time to sit down and fill out the density matrix, you get the same components that we had from the Liouvillean, so with optical pi pulse, and then the energy terms that keep the phase. But then you also have these potentials which change occupations due to thermal equilibrium, so that the temperature of the bath and the temperature of the electronic system, or the subsystem, are equal.
You mean phonon mediated or?
So Boltzmann rates. And so what we have is initially times 0, so we have our lowest state occupied. Just after some time, when you turn the temperature on, they'll come into a detailed balance.
I'm sorry for interruption. So I would say bye now. I will be there shortly.
Oh, okay.
Okay. Bye.
So two systems come into thermal equilibrium, and then we apply an optical pulse to try to invert the system. So you have changes in so you have a population inversion for a short amount of time, but then due to thermalization, these states will come back to their equilibrium, thermal equilibrium. So that's how the populations change. And then the off-diagonal elements, you'll notice that they spike in the same time frame, but then they dampen very quickly due to interaction. So they lose their phase due to interaction with the heat bath. And those are represented by these, well, I just call them gamma terms. So it's like a rate, a dampening rate. And that's kind of one way to define decoherence rate. So it's the rate at which those off-diagonal elements go to 0.
And big blue circles symbolize phonons.
Mm-hmm. With a distribution of
Frequencies.
Yep.
Physically, what is the mechanism of this decoherence?
The mechanism of coherence.
Of decoherence. What is it?
Well, it's just retaining a superposition of like your.
No, physically, what makes it lose coherence?
What makes it lose coherence?
Yes.
It's just average over ensemble or interaction with the heat path. So it's.
So
It just loses its phase.
let me take a pause, add a comment, and then you'll continue.
Okay.
So if we listen carefully, the concordant analyze last sentence of Aaron, it will contain two statements that decoherence can be contributed out of two mechanisms.
Well, that's what I missed. That's why I'm clear.
Interaction with thermal bus in sense of losing and obtaining a phonon quantum back on one hand, and an inhomogeneous mechanism when we do make an average over ensemble and one loses coherence as a result of destructive superposition. For analysis, they look like two different mechanisms, but for observables, they are hard to distinguish.
Okay.
Okay?
Sorry.
Please continue.
It's very late in the day for me. Fade.
Please don't faint.
Not faint. Fade. My mental acuteness. Acumen.
And then, so the expectations of, or the reason for going over these last couple of slides is, so we should get the expectation that coherence should slow down non-radiative relaxation rates because it can keep the superposition alive for longer, so you have less time for, so the rate that the system thermalizes is going to be longer. And just based on like all the equations I've gone through, it's not totally clear why that is. I guess that's just something that people have observed since people have been doing these dynamic simulations, that for systems that are kind of similar to how you'd model a perovskite, is if you don't include the, so if you make the dephasing like too quick, the radiative or the non-radiative lifetimes are a lot faster than what's seen in an experiment. And so, yeah, that's just the reason for going through the last couple of slides. And then now, so these are like the basis states that we'll use for our dynamics. So they're kind of busy and it's a lot. There's a lot of them, but I won't go through them all, but I'll just kind of give an idea of what the calculations I've been doing for these. So this is just the ground state. So without introducing polar ions, so this is just like my reference for comparing total energies. So there's not a lot interesting here. But then for my first system,
System or configuration?
or configuration of the same system. So initially, I just do, for optimizing the models, I do it all on spin polarized basis, so we can do different spin configurations of our polarons. And so this is like the SE-SH singlet that I call it. So you have your negative and positive polaron have the same spins.
And SE is not selenium.
Right.
Okay.
And then those are just illustrated in my density of states. So I cut out the band gap just to make things clear. But this is the whole state because there's not occupations at the band edge. And then the negative polaron occupying the conduction band edge. And then these were just to help me analyze the spectra, which a figure is kind of blocking up. But essentially the main takeaway is if you have some states occupied, it disables some possible optical transitions.
So if we go back one slide, in the lower right edge, there was a peak at 2.35 absorption peak.
Mm-hmm.
And if you return back one slide forward, this peak is absent.
Right.
So it bleaches out.
Mm-hmm.
Okay. Is it correct to call it photo bleaching?
Yeah, probably.
Okay.
And so we can do the same, or I guess I'm going ahead a step. And so then from the spin polarized calculations, I just do a single point to include spin orbit interactions. Because for perovskites it's important because the conduction band is filled with lead orbitals, so it has very high angular momentum states. And so it's important for making sure that the electronic structure behaves as it should. And so essentially the same figures, so I have hole state, electron state, or positive negative polarons, and then you do see some quantitative changes in the IR spectra between spin polarized and the spin orbit. And that's just mostly contributed due to a big change in the conduction band. So you get a lot of rearrangement of the energies. And so for the negative polarons, you get different contributions.
And this dashed line corresponds to?
So it would be optical transitions from here.
With almost zero frequency, just flipping spin. Can we say so?
Yes.
Okay.
So it would be like a quasi-degenerate transition.
Mm-hmm.
So this one here would correspond to like this state hopping to this state's similar in energy. Because since this is half filled, it means or implies it's degenerate, and so it could make a possible transition to something very close in energy.
Like if in spin polarized picture, it would be a transition from LUMO alpha to LUMO beta.
Mm-hmm.
Okay.
Or more or less, yeah. So that's the S, E, and SH polarons in the singlet configuration. But you can do the same thing. So occupying the same space, but just changing its multiplicity. So now the positive polaron has a spin up, and the negative polaron has a spin down.
So it is excite and flip the spin.
Mm-hmm. And so, just changing that configuration, you can get different possible signatures in your spectra. Because before this transition, I guess it would still be disabled. Doesn't matter. I guess just disregard what I just last said. But yeah, I'm not sure what I want to say. We can characterize the optical transitions, and then when you compare it to same configuration but including spin orbit, for the triplet we do see a very intense peak, where before it was near zero and lower intensity. But for the triplet, it increases a little bit in energy and is more intense. And for some reason, I haven't looked in depth into it, but before, like there wasn't this little hump out in this area. for the singlet. Whereas when you include the triplet, it must, like the unpaired spins creates like a magnetic effect, so it can break degeneracies. So I'm assuming that it's moving electronic levels around to create that additional hump. And that's where this optical transition comes from. So it'd be from here to here. Right, so for this peak to this peak.
So this transition will give the infrared triplet emission or whatever, absorption right now.
Yeah, absorption. So just by changing the multiplicities of the polon, we can see different spectra characteristics.
So how did you change the configuration for triplet?
So-
Using non-collinear calculations.
Right, so you can, when you do your spin polarized calculation, it's like when it writes into the like wave car and charge car files, it writes in like a magnetization, and then you use those to feed in to the spin orbit calculations. So you constrain the magnetism, which is like a analogous way to constrain the spin multiplicity.
So you're telling that when you run non-collinear VASP with only with no optimization, it inherits the spin configuration that you originally prepared with spin polarization in the same directory. So instead of playing with keywords in the in-car, you just inherit whatever configuration was prepared in spin polarized calculation.
Yes. Okay. But I have to modify the like occupations a little bit too. But the multiplicity is read in from an input file. So it's because I don't think you really can like change spin configuration with like a tag in the file or in the in-car.
Yeah, maybe, next time we will make knowledge transfer meetings. We may cover it in detail so that everyone can practice this skill.
I guess just as a note, it's like it's kind of ambiguous because it's well, not ambiguous, but like spin orbit coupling isn't a singlet or a triplet. It's like it's a combination of both of them. So it's if someone wanted to be aggressive, they could push that a little further, whether it's truly a triplet
So
or truly a singlet, but it's like components of what would be for the spin orbit wave function.
So you mean that in this spin orbit coupling, spin multiplicity is not well defined, observable, and it's just a conditional convention. Okay.
And reviewers haven't asked any questions yet, so.
Okay.
And then, yeah. So this is the same game, different electronic configuration. So now I keep the electron like in the S symmetry position, and then I just move the hole down to a P symmetry occupation. And so it's doing the same games, we're just looking at the possible optical transitions, whether it makes sense as I was doing these calculations. And in the density of states, you can see that the hole previously, if it was in the S, there would be a lack of occupation, the band edge, but then now the lack of occupation is in like this taller band. And so that's how all these figures tie together. And I don't know, it's probably not worth going through each one of these because there's 4 different possible configurations with 2 different multiplicities, so there's 8 configurations to go through, so it might be just a little too overwhelming to look through everything.
And if you plan to skip something, do you have a table or at least a verbal summary of all configurations? How would you like tabulate or call them or arrange them logically?
Well, I guess haven't yet, because some of them I still haven't processed the figures for. And also looked at like energy spacings. So compiling the data, or all the data, is still an ongoing process. So I guess the things to look for would be total energies, how total energies of each model compare to each other, looking more in depth at the IR spectra for each polar ion configuration, because that's one of the main things that we're interested in for the dynamics. So, in short, no, I don't have a table yet.
Do you have any teaching for us about most reasonable notation?
Reasonable.
Notation to symbolize each of the configurations. Like you're calling them PHSE triplet, and in the names of the files on the bottom of your slides, you use like alpha PH, beta PE. So it's could it be a universal Forde notation? Because it seems logical, but you may explain what it is.
The alpha beta one?
Yes, like
So it's-
combine both occupied, unoccupied, alpha or beta, S or P. So can you just introduce it and tell if it will cover all configurations that you need?
So it does. So I guess alpha just spin, so another name for spin up, spin down. And then pH and PE are the symmetry of the orbitals that I've been going through. So it's the occupations of the polaron. And then if it's just alpha symmetry label, it means it's same spin, so singlet. So, and then if it's alpha symmetry label, beta symmetry label, it's the triplet version. So that's how I've been categorizing.
So in your notation, you
So
have
there's an index for spin and there's an index for occupation
for both,
for both polarons. So there's 4 indices total.
and each of them can only take 2 values.
Right.
So the total number of configurations is 2 to the power 4, which is 16. And some of them will be repeating, referring to the same configuration.
I think
No?
I guess in total there's 16. But I guess I only do 8
Okay.
because I only do like you get up and down. But I only do like so it's like I don't change. I can always keep one as alpha and one as beta. Like I don't switch these 2 spots around.
Okay.
So there's 16 possible total. So I include the singlets and then some of the triplets. So all that, those will be inputs for when I eventually get to the dynamics for our model. So to do dynamics, you have to take our ground state models and implement 3 different aspects. So you have to, for doing molecular dynamics, you have to get them up to a temperature. So you have to heat them, make sure they get in some sort of equilibrium temperature. And I have that going for one model right now. And it goes fairly slow and it's pretty expensive. So for
How many years did it take to run these 100 steps of heating?
years?
Yeah. Half year?
Well, not a 12 year.
Okay, so a month for 100 steps. So like three
Essentially. Well, a
three
month,
ionic steps per day.
well, a month on like nurse time, so like up and down.
Okay.
Yeah. But it's, well, part of the problem was like it would do like 10 steps and then just die.
Mm-hmm. And then you restart.
Right.
Okay.
But then that's lost like 40 hours, like if it only ran for 8.
Mm-hmm.
So after 100 steps, it seems to equilibrate to the temperature I want. Which I
Do
define
you
as
plan to
zero.
do everything at room temperature, or you contrive plans to do backup mirror calculations at nitrogen, liquid nitrogen? I know it will be like twice as much calculations, but are there any reasons to focus on nitrogen temperature in the future?
One is that's what experimentalists can aim for, liquid
Uh-huh.
nitrogen temperature. And then for coherence, you'd expect like it'd be a good reference system to compare dephasing for two different temperatures, because there's definitely an expectation that dephasing should be longer at a lower temperature. So potentially, but it would be after I get all the other models going for couplings,
Mm-hmm.
since those are the priority. So that's heating. So that's just one of the models. And then from heating, you do molecular dynamics, and you get fluctuation charts. And it flipped them around on me.
Yeah, when going to Mac to PC and back, it always flips.
Did I always forget?
Behind you, did you?
I got 7 minutes.
Okay.
It only takes like
It's general.
4 to walk over there.
Okay.
Most of that's waiting for an elevator.
And so for this SH singlet, or the lowest energy polaron model, I have done 50 steps for molecular dynamics just to see how they look.
Mm-hmm.
And the fluctuations look, I don't know, typical. It's like a steady period of oscillation.
Mm-hmm.
So you could probably start running these for a longer time, because some of them I would try to start, but then the temperatures would wildly fluctuate. So I just have to heat it more to get it up to temperature.
But those intersections of the orbitals in the conduction band, are they suspicious or they are good things?
Ideally, you wouldn't want them.
So it is one of the reasons to do everything at liquid nitrogen, to avoid these intersections.
And I guess these are for molecular dynamics. They are done with spin polarized calculations. And so for quantum dots, you always have to worry about the surface and whether there's trap states that form during the trajectory. So those are more prevalent for spin polarized calculations.
Mm-hmm.
Whereas if you have spin orbit coupling, it reduces the band gap to like 1 eV. And so there's less chance of trap states forming just because the energetics are lower. So it's hard to tell directly from these charts how they'll go, but as long as I don't see like wildly changing spikes and fluctuations, and if I look at the empty video, as there's not like atoms flying off into different regions, that's staying intact. I don't have good reason just to abandon it.
I remember previously you have some spikes on your models, right?
Mm-hmm.
Why for this model there is no spike? And what's the reason for the spike?
I think, if I remember the figure you're talking about, I think it was with Spinorbit where those spikes occurred, and I guess I don't know. If I did look into it, I don't remember it off the top of my head.
But the model is the same, right?
Mostly, it's the same geometry for the most part. I've had to update it a couple of times because it likes to, like, the ligands like to float away. So I don't have too big of concerns, just from these 50 steps anyway. And molecular dynamics is relatively cheap too, so it's, if I have to redo them, it's not the biggest deal in the world. And the reason, or one of the reasons I'm worried, or talking about these fluctuations so much is, I guess I'm not very familiar with the theory. Someone named Mukamel wrote a book, and he wrote it in there. It's kind of what a lot of people use to calculate coherence times. But essentially, you can calculate coherence times from the energy fluctuations along a dynamic trajectory. And so it's essentially how much your energy, like the energy band fluctuates compared to the average over the trajectory. And so if you just do compute correlation functions, which we have scripts to do, is we can get these coherence times values and then get our dephasing rates. And so this J is like the overlap of state I with state J. And then the rate that this J goes to 0 would be characterized as the dephasing rate. Yeah, that's something I have to study more though, because this, I know, nonlinear optics stuff. It's kind of, well, it's not common in like classes, so kind of just have to sit down and study it. And then last is to compute couplings, which you compute on the fly, and I haven't got to them yet. But so then once we have our couplings, we have our I don't think of the word, but like population transfers. So the population transfer from I to J, and then from the fluctuations we can get the coherences between states I and J. And then there'll be a coding task to figure out how to merge them together along the same dynamics trajectory.
I do have. It's time for upload. I have a question right away. Each configuration does have specific equilibrium. Like each electronic configuration leads to specific nuclear configuration. And couplings with the orbitals of the same symmetry are expected to be different depending on what is the parent electronic and nuclear configuration. Can you develop on this statement and some expectations or something more than recognizing this fact?
You're talking something in this picture? Yeah, so I think what Dimitri was saying is you photo excite, so assume this is like your band gap, which has a certain geometry. And so you photo excite, you create your polarons, and then due to reorganization of the lattice, you have changes in spatial coordinates, and you also have changes of the energy. So for a polaron, it should become more bound. So you have a decreasing of this potential energy well for the negative and positive polaron. I think that was part of your question. I guess I don't know I can't remember what the other part of your question was.
Do you expect specific observations, specific physical effects from the fact that frequencies and couplings will be different depending on the parent electronic and nuclear configuration? For example, if you look for HOMO to LUMO non-radiative recombination, it could be different based on whether you are in APE, APH excitation or B PHBT. So the recombination rate will be different depending on which configuration system explores.
Right. Oh. I think I see your question now. So it's
And it could be the strongest part of this project
right.
at all.
So it's to do the D-dynamics, like I can't think of the technical term, but like along the trajectory. So if I started, so say I choose my initial conditions.
Mhm.
Don't know how we got there, but we somehow choose them. So we start with these occupations in the PE and SP states. So starting from these, it's use couplings from this electronic structure, and then as populations change, it's like you kind of just do a superposition of, so as the population of this SE transition increases non-radiatively, is to kind of have like a crossover point, or to do a superposition of your possible electronic states.
And then one may want to change to another set of couplings.
Yeah,
Okay.
so for, I guess it might be too tricky to do singlet and triplet at the same time, but you could do singlet and triplet like on separate trajectories. So you'd have 4 sets of couplings. So 4 sets of couplings, 4 sets of dephasing rates, and then 4 sets of like energy levels. Since we're explicitly including the excited states into the dynamics, because before we normally use a ground state approximation. So assuming that when we excite our model, that it roughly takes the same, that the couplings in the excited state will be the same as if you just use the ground state electronic structure.
Why you
Thank
would-
Aaron
Oh,
for
yeah.
presenting. So the talk is open for discussion.
Why you worried about where you gonna get your triplets?
So
I mean, you for the excite singlet. So is it going to flip into triplet through Spinorbit? Is this?
So, yeah, it's a good question. So, I think I would do 2 sets of trajectories. So I'd have one from like my triplet models. It's like I don't know how it turned into a triplet, but I'll just say that I just prepared it as a triplet.
Just does.
It's like, and I guess, yeah, because it normally does turn into like the lowest energy excited state is a triplet for quantum dots. So it's, once it eventually does get to the band edge, like it could be a triplet or a singlet. But I think I'll do the dynamics, just conserve spin, so spin doesn't change for either of them. So I'd do 1 set for just the triplet configurations, and the dynamics just for the singlet. Because, I mean, it would be possible to do like singlet triplets together, but then you'd have to account for conserving of angular momentum during the non-radiative rates. And I guess
I have no idea how expensive it would be, but you cannot include Spinorbit into your dynamics, right? Then it would become what?
You cannot.
Naive question. I'm sorry.
No. It would be too expensive to explicitly start from spin polarized bases and include both interaction with photons and spin flip mechanism. But if one starts with DFT orbitals that already include spinor orbitals, then it's not a big problem to run interaction with photons in bases of Kohn-Sham orbitals that already include hybridization, and or each orbital has percentage of like spin up, spin down. Does it answer your question?
Also, in a very general question, how do you know, you've got a polaron? If you photoexcite, I don't know, diamond, do you have polarons?
Very small polaron.
Okay,
Basically no polaron. But I guess I haven't done it for this model yet, but for just if you just put a negative charge into a box and let the lattice reorganize, we were able to see changes in the geometry. So it's like bond elongations, and then changes of bond angles. And when we actually did the dynamics,
oh my god, this is me.
we did see that the rates were slower for the polaron geometries. So it's qualitatively, the dynamics followed from what we'd expect with the model.
But I mean, in this formalism, it comes in naturally, right? You don't need to additionally worry if structure is soft and there are strong polaronic effects, then nature included, right?
For the molecular dynamics, yeah. So for our couplings, it would include like any anharmonicity.
Also, while you're up, if I may, so this structure is big enough that screening is strong enough so the excitonic effects can be safely neglected. Is this a fair statement?
I guess that's been an underlooked. I guess not underlooked, but normally it's like the polaron people who do this as a living. They haven't considered positive and negative polarons in the systems because perovskites are, I guess, kind of one of the first where it's like significant where people have to worry about it. So I saw one paper where they computed like the potential energy of the like a plus and minus polaron just along one axis, and they did find that there was like a minimum. So if you overlap them too much, it kind of reduces the polaronic effect, and then the Coulomb becomes just as significant, if not more. So
I believe you.
yeah. So essentially, if they overlap, they start to become more, or Coulomb attraction becomes more prevalent.
The dielectric constant of perovskites is rather high.
Yeah.
So it's electrostatic experiencing some screening.
You're talking about bulk or quantum dots?
It is known for bulk, but the mechanisms for the which are responsible for high dielectric constant are still in the quantum dots. There is a mobility of these cations. They're not chemically bound to anything. They're ionic and they are very mobile and
Yes, it's very squishy, this whole business.
respond to local change of electric field immediately.
I think in the box though, it's like polarons have like a certain natural size for whatever material they're in. So in some cases, it could be if you confine them, they have to overlap more, and so then you'd start to get some exciton effects.
So if you get to happen a reviewer of this work in the future, there are two killer questions. One, how come that one uses size of the quantum dot smaller than natural size of polaron? And second killer question, how can you speak about polarons if they exist in the same area of space?
Okay.
Typically one considers them to be way apart. If you were caring about approximations.
Now it's completely dark.
Fatima, you did have you plan to ask a question? While be online? No?
I'm good.
More questions? Okay, let's thank Aaron once again. So meeting is accomplished. If you were making any critical notes, please submit them to Aaron so that he can improve. And after some time period, he probably will repeat the same talk with add-on new results and improvements of definitions.
There were some comments from coming from television. Who were,
Fatima.
That was her.
No, she came in person.